So, what are we going to do today? I presume you have a final coming up that you're going to give me some review questions.
Yep. Mm-hmm.
Okay.
So the first, it wants us to rewrite as a rational exponent.
Okay.
So the cube root of x squared.
When you remove the radical sign, the numerator of the exponent is the power that x is being taken to. The denominator is the root.
Okay.
So, let me give you an example. Always do the root first. So what is 8 to the 2/3 power?
That would be 8 squared.
Do the root first. It'll be simpler. You'll deal with much smaller numbers if you always do the root first, the denominator.
So the square root of 8.
The cube root of 8.
Okay.
Is what?
So that would be 2.
Okay, and then 2 squared?
4.
See, we never dealt with a number bigger than 8. Whereas, had you squared it first, then we'd have been taking 64, the cube root of 64, which is still 4, but it's harder to figure out. And all of the problems they give you like that are always like that, where if you take the cube root first, you'll get an integer. And then it'll be easy to go from there. All right, what else?
So the next one, it wants us to rewrite as a radical.
Okay.
It's x plus 5 to the 8 over 11.
All of it to the 8 over 11?
Yes.
Okay. How are you going to do this? We know there's a radical sign. Let's go ahead and put that in there.
So 8 would go out.
No, the root is the denominator.
Okay.
So that's the 11th root. What goes inside the radical sign?
X plus 5 to the 8th.
Yeah. It's as simple as that.
Okay.
Just always make sure that the denominator is the root and the numerator is the power.
Okay. So the next, it wants us to evaluate each expression.
Okay.
And the first one is the 5 root negative 32.
5th root of 32?
Mm-hmm. Negative 32.
What's the 5th root of positive 32?
That would be, I'm not sure.
Good to know your 2's. It's good to know all the way through the least the 5th root.
Okay.
4, 8, 16, 32.
Okay.
So what is the 5th root of 32?
2.
What's the 5th root of minus 32?
Negative 2.
And it is not plus or minus. It is negative. Odd roots always give you both positive and negative solutions. Even roots, only positive.
Okay.
Okay. In other words, if I had the square root of 4, I technically have plus or minus 2.
Okay.
Now, let me amend that a little bit. When I write the square root of 4, this means the positive square root.
Okay.
Okay? However, if I have an equation like this, and I'm solving it by taking the square root of both sides, then my answer is plus or minus 2. Always. It all depends on whether you're solving an equation by taking the square root or you're looking at that. That means plus 2. If I want the minus 2, I'm going to write it like that. That means minus 2.
Okay.
Okay? All right. What else?
So the next one is 16 to the 3 over 4th.
Okay? It's first step.
We'd want to take 16 to the 4th root, which would be 2.
Okay?
And then cube 2, which would be 8.
You got it. That's the way.
So the next one is 49 to the negative 3 over 2.
What do you do with negative exponents?
You put the whole equation over 1 over the whole equation.
Okay, tell me what to write.
So 1 over 49 to the 3 over 2.
You got it. Now, what is 49 to the 3 over 2? The denominator first, the square root.
49 squared would be 7.
The square root of 49 would be 7, and then 7 cubed.
That would be 343.
That's the answer.
Okay.
Okay. There is an interesting problem that I'm going to show you, and I'm not going to be able to explain it. What do you suppose that is?
That would be negative 2? No.
Take the cube root first.
Okay, cube root. Yeah, that would be, negative 2.
Okay, and then square negative 2.
4.
Looks simple enough. Are you familiar with Wolfram Alpha?
No.
It's considered like the highest math database in the world almost. Put that in Wolfram Alpha, you do not get 4. You get 3 plus some number, you get the imaginary. Or you get 1 plus 3 point something times I. And the reason for it is very strange. Like I said, I wish I could explain it, I cannot. But when you take negative numbers to fractional exponents, be careful.
Okay.
Okay? They probably won't give you like anything like that because that's somewhat of a trick question. Okay? So they'll always give you a positive base, I'm sure. If they do give you a negative one like I just did, just go ahead and do it naturally. Do the denominator first, then the numerator. In other words, you would come up with 4. And that's what they would be looking for. But from a pure mathematical point of view, it's not necessarily a true statement.
Okay. So the next one, it wants us to tell the transformations of each function and then state the domain and range of the transformed function.
Okay.
So the first one is f of x is equal to 5 and then root x minus 6 plus 2.
Let me guess, it's like that.
Yeah.
Okay. Whenever you're dealing with transformations, you have to figure out what your parent function is. Your parent function, there's only about 8 of them, elementary functions. Y equal x, y equal x squared, y equal x cubed, y equals square root of x, y equals sine of x, y equal cosine of x, y equal x to the 1/3 power. There's pretty much all of them. Which one is this?
This is y equals x square root of x.
Y equals square root of x. So the first thing we want to do is graph that. Now, if you should try to memorize the graphs of all of your elementary functions. This one looks pretty much like that.
Okay.
Notice the domain is only x greater than or equal to 0, and the range is only x greater than or equal to 0.
Okay.
That's why it starts at the origin and is only in the first quadrant. Now, the priority that you apply your transformations, it does not matter the order you do it, except if you have a reflection. If you have a reflection either over the x-axis or over the y-axis, you have to do that first. Otherwise, you don't end up with the correct graph.
Okay.
So, I can do these in any order I want. We have 3 transformations. We have that, we have that, and we have that. What's the 5?
5 is stretch.
Vertical stretch. It's vertical because it's outside the function.
Okay.
Outside the radical sign. What is the 6?
It's left 6.
It's horizontal or vertical?
Horizontal.
Yeah, I don't know if we've ever talked about this before, or whether it's being in horizontal or vertical. I find that it's much easier to memorize them if you do it that way, because there are only 6 transformations. There are 3 horizontal ones and 3 vertical ones. And one of each of those is a reflection. So really the only thing you have are stretches and shifts in the way of transformations that are not reflections. Okay? So first of all, this is inside the radical sign. That makes it horizontal. It's being subtracted. That makes it a shift by 6 units. But the standard is always x minus h. So it's 6 units to the right.
Okay.
In other words, it's always the opposite direction of what you would think it would be. Because that looks like it would be to the left because of the negative sign.
Mm-hmm.
But it's to the right, so I'm going to take the only point I have, and I know for sure, and I'm going to shift it. So this function right here is y equal root x minus 6. I'm only going to apply one at a time. Okay, that's that one. Now let's apply the next easiest one, which is the plus 2. What is the plus 2? Is that vertical or horizontal?
Vertical.
And what's it do?
It goes up 2.
Yeah, and shifts do not change the shape of the curve. The minus 6 didn't change the shape. The plus 2 isn't going to change the shape. I'm just going to take my one known point, move it up 2, and try to draw the shape exactly the same.
Okay.
Okay? So that green is f of x equals root x minus 6 plus 2. So the last thing we have to apply is the 5. And it's the hardest one. Is it vertical or horizontal?
Vertical.
Is it a stretch or a shift?
Stretch.
Okay. Now a stretch does change the shape of the curve. And where am I going to put my initial dot? Where the green dot is now, where is my next color dot going? That green dot, incidentally, is at 2.
It's going to stay where it is, right?
No. Excuse me. No, actually, yes, you're absolutely right. It stays exactly where it is.
Okay.
Okay. But everything else gets shifted. Excuse me, stretched. So it changes the shape, becomes steeper.
Okay.
Whereas the blue and the green and the red were a little flatter. So this has been stretched upwards vertically. And that's the final answer for all 3 of these transformations. Okay? I always think that unless you're really good with transformations, in which case you can do all 3 at once, but if you have any doubts whatsoever, then I recommend doing them one at a time. Whatever you end up with is what you get. Just make sure you do any reflections first. And it doesn't matter if you got 2 different reflections, you can do them in whatever order you want, just do them ahead of all the other stuff.
Mm-hmm.
You got next.
And then, so it wants us to state the domain and range.
Okay. Let me write it again. What's the only strict restriction on domain? When you're thinking about domain, usually domain is all real numbers. Okay? When it is not all real numbers, the task really is to figure out what it can't be. In other words, if I say this, what's the domain of that? Well, it can't be negative numbers.
Mm-hmm.
So x would have to be greater than or equal to 0 automatically. If I just say y is equal to x, well, x can be anything, all real numbers. With me?
Yeah.
Okay. Well, when I have something in the radical sign different than just x, take whatever's in the radical sign and make it has to be greater than or equal to 0. Now solve that inequality. What do you get?
X has to be greater than or equal to 6.
And that's the domain. Now, have they requested you do this with interval notation?
I don't think so.
So
actually, yes.
Satisfactory?
Yeah.
If I were to do interval notation, it would be bracket 6 comma infinity parentheses.
Okay.
In other words, the fact that it's greater than or equal makes it a bracket. And infinities always have parentheses next to them.
Okay.
Okay. So we know that x has to be greater than or equal to 6. And that's the only restriction. The 5 isn't going to place a restriction on it, nor is the plus 2. However, when we come to range, if you'll remember what our curve looked like, the final one, and this point was 6 comma 2. You can figure out the domain from looking at the curve, right? In other words, there's no x value to the left of 6. There's only x values greater than 6, and it's going on forever in that direction.
Mm-hmm.
Okay? So you can figure out the domain looking at the curve. It was just almost easier to figure out the domain by just saying x minus 6 had to be greater than or equal to 0 and solving it. The range is a little different. The range is actually easier to figure out by looking at the curve. What does y have to be?
Y has to be greater than 2.
Greater than or equal to 2. In other words, that is a solid dot. Y can be 2. Where would y be 2? How about if I let x equal 6? Then y equals 5 times 0 plus 2, meaning plus 2.
Okay.
There's no way y can ever be less than 2, because you cannot ever make that a negative number. The square root of a number is always positive. Multiply a positive number by 5, you still have a positive number. So, and then add 2, that's why it always has to be greater than 2. This can be 0, but it cannot be less than 0. So that whole thing that I have circled has to be greater than or equal to 0 also.
Okay.
So if I were going to figure out the range without looking at the graph, without having graphed it, well, I would just have to figure out that this, the lowest that can ever be, is 0. It can't be negative. And when it's 0, y is equal to 2. If x is any value greater than 6, then this is a positive number added to 2. So I can kind of figure out by looking at it algebraically that y has to be greater than or equal to 2, because all of this stuff to the left of the plus 2, the biggest that can ever be is 0.
Okay.
Excuse me, the smallest that can ever be is 0.
Okay.
Okay? You don't probably have to worry about that if they're going to ask you to graph all of them anyway. And you'll always be able to look at the graph to figure out the domain and range.
Okay. And so it's like the same thing, and this time it's f of x is equal to negative 3 over 4 square root x minus 3.
It's a parent function.
Its parent function is y equals the square root of x.
Now when I draw it like that, that's a solid dot. If that was a transparent dot, then it would not be able to be 0. But the fact that I've made it a solid dot means x can be 0 and y can be 0. Okay? So, I see a minus sign right there. That's a what?
A reflection.
What kind? Is it horizontal or vertical?
Vertical.
Yeah, because it's outside the radical sign.
Mm-hmm.
Vertical means what? A reflection over which axes?
The x-axis.
Exactly. And you can see why that's a vertical reflection.
Mm-hmm.
I just flipped it vertically. Okay. So this one, doing it one step at a time, is y equal a negative square root of x.
Okay.
Now the other two things we can do in whatever order we want. Let's do the 3/4 first this time. What's the 3/4 do?
That's a vertical shrink.
Yeah, which means instead of being like this, it would be more like this.
Mm-hmm.
Where every point that was on the blue curve is now 3/4 of the green curve is 3/4 of the distance to the x-axis that the blue curve is. It's basically what it says. And the effect is to change the shape and to be a shrink. It makes that curve flatter. Anytime you have a number right here between 0 and 1, it makes it a shrink. If the number is greater than 1, it makes it a stretch. And it doesn't matter whether there's a minus sign or not in front of it. It all has to do with the absolute value of that 3/4, whether it's between 0 and 1 or greater than 1.
Okay.
That's what determines whether it's a stretch or a shrink. Vertically. When you're going horizontally, it's actually the opposite. When it's greater than 1, it's a shrink. When it's between 0 and 1, it's a stretch.
Okay.
Just remember they're opposite. Vertically is the one you generally are dealing with. Okay, there's one last thing. What are we going to do?
We're going to move it to the right 3.
So I take my point, move it 3 units, and draw a curve that's basically trying to be parallel with that green curve. If curves can be parallel. They can't really, but I think you know what I mean. Okay. And so that blue is the final result. What's domain?
The domain is x is greater than or equal to 3.
And the range?
All real numbers.
Look at the blue, the light blue curve. Does it go up above the x-axis?
No. So
No.
x
So
will
it's
be
never positive.
less than or equal to 0.
And that's where it always lives at either 0 or less. And this thing does not flatten out. It keeps going down to negative infinity.
Okay.
In both directions. Whether I'm looking at this one or this one. If you go far enough to the right on the x curve, on the x-axis, you will get to infinity, one side or the other. It's not always obvious from this graph that that's the case. Okay, what else?
So the next one is f of x is equal to cube root x minus 9 minus 1.
It's the parent function here.
F of x is equal to the square root of x, or y is equal to the square root of x.
Cube root of x.
Okay.
Okay. In other words, the cube root of x is a elementary function also. So is the 4th root, so is the 5th root, so is the 6th root. They're all elementary functions. The only one they really give you at this point in algebra is the square root and the cube root as elementary functions. Okay. Now, another elementary function is y equals x cubed. And I can always remember what that one graphs like. Looks like that. So that's y equal x cubed. Notice that this is the inverse, y equal cube root of x. And inverses are discovered by reflecting about the line y equal x, which is that red dotted line. All inverses, all, no matter what you're talking about, including calculus, all inverses graph as a reflection over the line y equal x. Okay, so how do I reflect that? Basically, anything, in other words, this part of it will go like this. right? And this part of it would go like this. So the blue line is the elementary function y equal either x to the 1/3 or cube root of x. Both are the same.
Okay.
Okay. And again, this eventually gets to negative infinity on the y-axis.
Okay.
As the right side gets to positive infinity. Because if you look at this elementary function, x can go to infinity, right? In both directions, negative infinity to positive infinity. You can take cube roots of negative numbers. You just can't take square roots of negative numbers. And if x goes to infinity, what's y going to go to?
Infinity.
Yeah. And if x goes to negative infinity, y is going to go to negative infinity. Okay? So we're not quite done with the transformations yet. We didn't cover the -9 and the -1. Okay, so let's do those in a different color. Let's start with the -9. What does that do?
That moves the graph, the line to the right 9.
Okay, so I'm going to try to take this blue line and draw it about that point. The right-hand side goes like that. The left-hand side kind of goes like that.
Okay.
So that green line is the cube root of x minus 9. What's the last thing we have to do?
The last thing we have to do is subtract, make the line go down by 1.
Vertical shift down by 1.
Okay.
Okay. And notice that we only have one point to work with here. And starting with the red line, the only point I had was the 0, 0, the origin I knew was in there. Same with the blue line. But once I moved it, once I shifted it to the right, I shifted that point 9 units to the right. So this is the key point, the only one I have to move. I don't know what this point up here is. And I don't know what this point down there is. But okay. I'm going to move this down 1 unit. So it's going to start right there. So what are the coordinates of that?
So that would be 9, -1.
And it's going to look just like the green. It's going to be as parallel as I can draw it because we're dealing with a shift which does not change the shape.
Okay.
So that orange line is the final graph. Now, domain.
So the domain is x must be greater than or equal to 9.
Look at that orange curve. And force your eyes to look left to right. Where's the left side headed?
Past to negative, like to negative x, negative infinity of x.
Infinity. Where's the right side headed?
Positive infinity.
In other words, x can be anything we want. There is no number that I cannot plug in for x. Only because you can take cube roots of positive and negative numbers. In other words, there's no rule that says x minus 9 has to be greater than 0. It can be greater than 0, equal to 0, less than 0. Okay? Now, by the same, rather than trying to figure out the answer from algebraically thinking about that, look at the graph. What's the range?
The range is
Force your eyes to look up and down, not left and right, but up and down.
So, negative infinity to positive infinity?
Yep.
Okay.
Is that on your end? No. That bell I just heard?
Oh, I think that was on my end, yeah.
Okay. All right. So that's how you do that one.
Okay.
All of these, the key is figuring out what the elementary function is and then just figuring out what each translation does. Or
Okay.
transformation.
Mm-hmm. So next is the same thing.
Okay. Since you're preparing for a final, I will let you direct. We've got about 20, 25 minutes left. So I want you to pick the stuff that you want to cover the most important 25 minutes.
Okay.
If you've got these transformations down, then let's not keep doing them. If you're not sure you got them down, well, then let's do another one. But if you're sure you got them down, then let's go on to something else.
I think maybe let's do one more transformation, and then I'm going to go on to something else.
All right.
So it's y equals -4 x minus 1 cubed minus 2.
Did you mean that?
Oh, cube root. Sorry.
So it's -4 cube root of what goes inside the radical? I'm sorry.
X minus 1.
Okay, and then outside the radical?
Minus 2.
Okay. So again, and you realize that f of x is the same as y, right?
Mm-hmm. Yeah.
They're interchangeable.
Okay.
The advantage of f of x is that it tells you it's a function in x. In other words, the only variable I'm going to see on the right side of that equal sign are x's. I'm not going to see any y's or r's or t's or anything. And I can also plug in a number for x. If I want to evaluate this function at x equal 2, then I can say f of 2. So the f notation is quite a bit more robust than the y notation. But you have to write 2 letters also. So when I talk about elementary functions, I just write it in terms of y. What's the elementary function?
Y equals cube root of x.
And again, I know how that goes now.
Mm-hmm. So, yeah.
Pretty much like that. That's probably not very good drawing of it, but it'll have to do. What I got 1, 2, 3, 4 transformations. Which one do I do first?
The negative.
What does that do?
That reflects it over the vertical, over the x-axis.
Okay, so if I draw that reflection, get something like this. So this is y equal negative cube root of x. The order that I take the rest of them does not matter. Let's do the 4. We'll just go from left to right.
Mm-hmm.
What's the 4 do?
That stretches the function.
Okay, I'll do that in green. It doesn't shift it anywhere, so I still have my center point there. Just makes it a little steeper on that end and a little steeper on that end. So the green is now y equal -4 cube root of x. Wow, that green is really not a good color, is it? Oh, that's because I was hitting the wrong button. Yeah. I'll use this green this time. So next thing to apply?
Next would be the -1 and the x minus 1.
What does that do?
That shifts it to the right 1.
Okay. Again, take the only point you have and try to draw a curve parallel to the previous one. Okay. So now that is y equal minus 4 cube root of x minus 1. One last thing to do.
The minus 2, so move it down 2.
Something like that. Okay, now, really the easiest way to come up with domains and ranges is to, if you have a graph, to just look at your graph. What's the domain? The orange line.
Negative infinity and positive infinity.
Yeah, and there's 3 ways you can write that. That's one of them right there, all real numbers. You can also write it as interval notation, like that. And you can also write it as x is greater than infinity and less than, greater than negative infinity and less than positive infinity. All 3 of those are legitimate ways to write the domain. They all tell you what x can be. Okay? Range.
The range would also be negative infinity and positive infinity.
Yeah, we'll just write it like that. And there, you got to be a little careful here, because the way I have drawn the orange graph, it actually does look like it's approaching some horizontal asymptote. Wouldn't you agree? It looks like it's flattening out, as opposed to always going north.
Yeah.
It's always going north.
Okay.
So it eventually gets to positive infinity on top and negative infinity on the bottom. Now, you do have to be a little bit careful. There is such a thing as a logistic function that does flatten out and approach 2 horizontal asymptotes. In other words, this logistic function that is the first one they give you after the elementary functions, this logistic function cannot be stated as a transformation of one of your 8 elementary functions, but this truly does have an upper limit. In other words, if that's 5 to minus 5, the range on this function is minus 5 to 5. This curve never goes above that dotted line or below the dotted line. So there are functions out there that look a lot like cube root functions. This looks exactly, I've drawn it almost indistinguishable from cube root function, but it's actually a logistic function. So it doesn't go all the way north and all the way south. Okay? So it depends on the function, not necessarily the appearance of it on the graph. Okay, what else?
So how do you find finding inverses? So
give me a function, I'll show you how to get its inverse.
f of x is equal to 7x plus 3.
In this case, they actually make it a little more difficult by using f of x notation. So the first step is really to switch to y notation.
Okay.
What's the next step? Because a lot of times they'll give it to you in y notation.
Mm-hmm.
So what's the first, or in this case, the second step to finding an inverse? Switch the variables.
Okay.
And the last step is solve for y. And that will be the inverse. It will not be the same y as that y, because I just switched the variables. So when you solve for y, what do you get?
x minus 7, y equals x minus 3 over 7.
That's the inverse.
Okay.
All right. Now, if I didn't want to switch the variables, there is another way that maybe is a little better to do this, because I hate having a y that means two different things. Okay, so instead of switching the variables, I'm going to switch the variables and call it f inverse. So my first step would be this: x equals 7 times f inverse of x plus 3. Same as before, only I'm not using y. I'm using f of x, and after I switch the variables, I turn it into f inverse of x. Now, when I get done, I don't have any notation problems at all. That's exactly what f inverse is. In other words, I don't have two equations where the y is different meaning than the other y. So, personally, I would almost suggest always turning it into y as your first step and then going from there, and the final y you get will be the inverse function. It just won't be the same as that initial y. Okay?
Okay.
Hope I didn't confuse you with that. I rarely give people this analysis. Although the more I do it, the more I like it. Because I don't have, in other words, every place that is f of x means f of x, and every place that says f inverse of x means f inverse of x. All right.
So, how to find the inverse of g of x is equal to x to the 5th plus 1.
You tell me how to.
4x to the 5th. 4x to the 5th, sorry.
4x to the 5th?
Yes.
Is the 4 to the 5th power or just a coefficient?
Just a coefficient.
Okay. So what am I going to do?
First, turn the g of x into a y.
Okay.
Then switch the x and y. Then subtract 1. Then divide by 4. And cube, get the, do like 5th root.
5th?
Yeah.
That's exactly what I would do like that. And I could do it with a radical sign, or I could take that whole thing and make it to the 1/5 power.
Okay.
Either one. Okay.
So, let's see. How about expanding? Okay, so
Okay.
I need to expand this. So log 5, log 5th, w squared over y.
Okay. The way I pronounce this is log base 5 of w squared over y. Where w squared over y is the argument.
Okay.
Just for terminology. I don't even know if that's the official terminology. That's what I call it. Whatever you're taking the log of, that's the argument.
Okay.
Okay? And you're taking the log of something. You're not multiplying log by that. It's kind of like the f of x. F of x does not mean f times x. It just means you have a function of x.
Okay.
This means you're taking the log base 5 of w squared over y. So Do you know how to do this?
So first, we would want to.
You're going to split it into two different log functions.
Okay.
What are they?
So it would be 2, or no.
Base never changes.
Okay.
In fact, if it's a different base, you can't do it. It has to be the same base.
Okay.
So I'll give you a hint. What goes next?
Log base 5.
Is it an addition or a subtraction sign?
Subtraction.
Correct. Whenever you have division going on in the argument, you're going to be subtracting the log. Just by your rules of logs. Now, there's one last expansion that you can do here. And that's to take that exponent and move it down in front. You can always do that.
Okay.
So you get, and that is also part of an expansion. You want to make sure you do that part. And when they ask you to compress, that's the first step instead of the last step. In other words, when compress, if they'd have said compress that, the first step would have been to take that 2 and stick it as an exponent over w, and then combine it to one log function to get back to what you started with.
Okay.
So the order you do it is exactly the opposite, depending on whether you're expanding or condensing. And you're going to have an equal amount of each.
Mm-hmm.
In other words, if you got 5 condensing problems, you're going to have 5 expanding problems also. They consider them equally important.
Okay.
Both directions.
And so next is find the coterminal angle of negative 1,205 degrees between 0 and 360 degrees.
Okay. So they want theta to be between 0 and 360.
Mm-hmm.
Coterminal angles, you can always add multiples of 360 or subtract multiples of 360. Okay? So what I'm going to do is I'm going to keep adding 360 until I get within 0 to 360.
Okay.
Okay? Well, I can tell I need at least 3 of them. In fact, I'm going to need 4, but there's at least that one, and that one that's only going to get me still to a negative angle. So I got to add another one. Well, 1440. So it's this plus 1440. What does that give you?
That gives me 200. No, yeah, 235.
There's your answer. That is the coterminal angle that is within the unit circle.
Okay.
So how do you figure out how many you have to add or subtract? Just kind of have to look at it and keep adding them until you get it to be a positive number.
Okay.
If it was plus 1205, then I would just start subtracting 360s until I get it within this range. Well, I can tell that if I subtract 3 360s, that's 1080. And I am subtracting, and that would give me 115 degrees. So that would be the coterminal angle if they'd have started us on plus 1205. So you add or subtract multiples of 360 until you get it within between 0 and 360.
Mm-hmm.
And that's it. That's the only thing you have to know.
Okay. And so, I'm going to go back to expanding.
Okay.
So it's so it's ln. How would I like say that?
Natural log.
Natural log.
And what the natural log is log base e, where e is equal to this number 2.71. Second most important number in all of math after pi.
Okay.
Okay, so instead of always writing log base e, they've come up with a 2-letter designation, natural log.
Okay.
And it also, natural log is the only log you deal with once you get to calculus. All the other logs become insignificant. Natural log is hugely important in calculus. That's why they have their own little 2-letter designation for it.
Okay.
All right, but all the log rules apply as long as all of them are natural logs.
Okay.
So what's the argument?
Natural law of 36x to the 7th. And it's not over anything, so.
All right.
Wants us to expand it. So first it would be natural log.
Do the separation first, wait to the last to bring that exponent down.
Okay. Natural log 36.
Multiplication is going on, so it's natural log of 36 plus what?
X, natural log 36, natural log x.
X to the 7th. Now what's the last step?
Bring the exponent forward.
Okay, so it becomes natural log of 36 plus 7 natural log of x. And the reason you do it last is because it can get confusing if I do it first. If I do it first, it's going to presume that the 36th is taken to the 7th power also, and it isn't being. It's only the x that's being taken to the 7th power. Unless the whole thing was in parentheses, and then I did it wrong. But as long as I've written it properly, this is the right way to do it.
Okay.
Just always maintain the order that when you're expanding, do your separation first, and then bring down your exponents. Just like when you're contracting, do your exponents first, and then everything else after that.
Hello?
Can you hear me? Wow. Huh. John?
Oh, yes.
Yeah, okay, good. I'm glad I didn't lose you because my phone is just about out of juice, so I wasn't even going to be able to call you. But we got disconnected there. The audio went out on us. But we're at the end of our session time anyway. So
okay.
That's probably a good place to stop. Unless you have any final questions, I'd be happy to
I don't think so.
Answer them. But good luck to you and have a good summer. What are you this year? What grade?
I'm a sophomore right now.
So you're going to be a junior next year?
Yes.
What are you taking? Do you know?
I think precalculus.
Pre-calc trig? Or just pre-calc? Probably pre-calc trig. But anyway, good luck. And if I can help you next year, I'll talk to you then. I think we lost the audio again, but I'm going to go ahead and just hang up if you can hear me. Have a good summer.
Okay.
Bye-bye.
Bye.